Hello there, my name is Adam Sweer. I'm the Vice President and Project Manager of the ASME chapter at VCU. My primary objective was to work with each of the design teams to ensure that they were efficiently working towards their goals to create the drone.
Hi, my name is Michael Vo and I am the frame team captain for VCU ASME. The main objective of our team is developing a lightweight, cost-effective, and strong frame for the drone. We developed this frame using SOLIDWORKS and its main features like topology optimization and its ability to create a mesh body to create a Veroni top.
Hello, my name is Anthony Rubio. I am the team captain for the electrical team at VCU ASME. Our team responsibilities included sourcing all of the electrical components and ensuring that they were properly connected in the final series.
I'm Fadel Haji, the Flight System Team Captain for VCU ASME. The main objective of our team is to calibrate the drone so that it will be safe to fly. The calibration process was done using the Betafly software. We programmed the switch to switch between two cameras, another to turn on and off the electromagnet, and one more as a failsafe in case anything goes wrong. All of these features will be controlled using the remote controller. We also calibrated the ESCs and throttle control so that the drone can fly smoothly.
My name is Finn Cow and I am the payload team captain of VCU ASME. My team's main objectives is to create a successful payload security mechanism, and we do that by researching and designing ways to pick up and drop off the payload, while at the same time capturing the whole process by designing a camera mount, which is a part of the whole system.
For our design, we decided on a modified X shape due to its stability, efficient use of space, and there's a lot of literature online to help us create our frame.
SOLIDWORKS was used to develop each of our individual iterations. Several of the iterations were all virtual through SOLIDWORKS and Google Drive. Further into the design iterations, we decided to base our design around the maximum allowed constraints per the competition rules, which were 33 centimeters motor-to-motor center distance and a 4S battery. We then primarily used topology optimization in the design of the frame, where we applied the simulation program within SOLIDWORKS to our rough, bulky shaped components. After applying the various load values that each piece of the frame would be subjected to, such as weight, lift, and torsion, the topology optimization provided new parts that were shaped to be the most weight efficient, while also allowing the parts to remain within their force requirements. We then printed our first physical iteration in PLA for its low price, simply to test each of the mounting points of all of the hardware. From that PLA model, the final iteration was created with final hardware mounting adjustments made and a base made from nylon carbon fiber filament for the most strength and reliability. We also then applied a unique Veroni design to the top cover for aesthetics and weight savings.
Noteworthy design features in our final iteration include the Veroni design for the top half of the frame. This process included converting the initial solid body into a mesh connecting all the faces, and a circumference was added to these connecting lines to give the resulting frame design you see. In designing the arms, we used topology optimization to incorporate two breaking points in the arm meant to protect any electronic components of damage in the case of a minor or a severe crash. We also added a channel into the top of the arm for wires to fit flush into and prevent dangling wires surrounding the frame.